Hello, good morning friends. We are here in the concluding lecture on rate processes. So in this series of lectures, what we have learned and what is the hope, so that we should have an overview on that. So in this pieces of lecture, so we this is the outline that we started with. We gave this outline at the very beginning that this series of lecture will have like these topics, mainly reaction rates and rate laws. We already discussed on this. Then effect of temperature on reaction rate, another topic, that is how temperature is going to affect the reaction rate. Then we went to complex reactions, that is reactions can be simple, may be complex. So we discussed examples of complex reactions and their corresponding kinetic descriptions. Then theories of reaction rates, then kinetics of some specific reactions, we dealt with that. Then catalysis is a very important thing, very important aspect in especially in chemistry, industrial chemistry, biological chemistry, and many places catalysis plays a very crucial role. Okay, so we discussed on that. And catalysis like biocatalysis we also discussed. Then we talked about introduction of fast reactions, the reactions which are completed in a very short time, like in a moment like maybe within say 1 nanosecond maybe, or maybe 1 millisecond, okay, millisecond or even less than that, maybe in microsecond. Okay, so faster than nanosecond like picosecond or maybe femtosecond, those are under ultra fast processes, but fast reactions could be like millisecond, microsecond, like that. Okay, so means those fast reactions are very difficult to probe. So we talked on how to follow those reactions. Okay, then reactions in solution, ultra fast processes we discussed, and finally we dealt with reaction dynamics. Now the textbooks which was which I recommended, apart from these books maybe you can consult other textbooks as well. Okay, or maybe good physical chemistry textbooks you can follow. One is that I recommended is Chemical Kinetics and Reaction Dynamics by Paul Houston. Then Chemical Kinetics and Dynamics by Steinfeld, Francisco and Hayes. Third one was Principles of Chemical Kinetics by House. Then Tutorials in Molecular Reaction Dynamics by Valance and Broward. It's a nice book. And Molecular Reaction Dynamics by Raphael D. Levine. So these books you can consult. Apart from these books, you can consult other textbooks as well. Okay. Now, why is chemical kinetics? Because chemical kinetics affects everyday life, and it determines how fast insects walk, how quickly plants and animals grow, and even how fast hair grows on your head. So this everything, I mean everything is related to chemical kinetics, okay, or maybe biochemical kinetics. It is very important in chemical processes. Selectivity, activity of chemical reactions determines how well chemical processes will work. Okay, so very important. That's why it is a very important topic. In process chemistry, like what reactions can lead to desired products, what side reactions are possible, is it going to affect the main reaction of our interest, yes or no, or if it is there, how to get rid of that problem. Okay. And also, of course, what are the rates of such processes. Okay. Next is conditions, which is very, very important, whether the reaction is possible in gas phase, whether the reaction is possible in aqueous phase, non-aqueous phase, and so on. And if the reaction is possible, then what are the factors that are responsible for controlling the rate of the process, that is factors on which rates are dependent, okay, like temperature, pressure, concentrations, okay. How this is going to affect, these are going to affect the reaction, that is reaction condition. Also solvents, very important. Next is catalyst. If this reaction is catalyzed, then whether it is a normal catalytic reaction, then it is an autocatalytic reaction, or maybe if there is a poison for the catalyst, that we should also know. That suppose because of some secondary agent, this catalyst are poison, so reaction rate is decreased. So these are the things that we should look into, and these are the parts and pieces of chemical kinetics and rate processes, especially rate processes, because we are dealing with rate processes in chemistry. Rate processes could be some other places also, some other subject also, like physical rate, that we are not going to discuss out here, okay, that is rate of flow of something, that we are not going to discuss over here, like flow of material, okay. So maybe we are not here. What we are interested in is everything, means everything related to rate processes in chemistry and chemical systems, okay. The adjective kinetic originates from Greek kinetikos, that in turn originates from Greek kinetos, which means moving. So it is something moving. The word kinetics is used in physical and life sciences to represent dependence on time, dependence of something on time, dependence of in physical science, or maybe chemical sciences, so dependence of something on time. In physical science, in chemistry, dependence of concentration. Chemical kinetics or rate processing is in chemistry is a branch of chemistry that is dealing with rate of change of concentration of reactants in chemical reactions. So that is that what we are going to learn. I mean, what we already learned in this series of lectures. Okay. So then we also discuss this point. I mean, thermodynamics and kinetics, is there any tussle between them, whether thermodynamics is more important or kinetics is more important? Okay. Apparently it looks like thermodynamics controls everything, okay, but at the same time we should remember that even if a process is thermodynamically feasible because of its very low speed, I mean very low rate, maybe the substance is not degraded. Okay. So, that is why kinetics and thermodynamics for a chemical reaction, these are somehow interlinked together, okay, like two parallel threads running parallel to each other. Okay. Reactions can be one of the following, like I told, that which is not thermodynamically favored, reactant favored, thermodynamically favored, which is product favored, but not kinetically favored, which is basically a slow process, or kinetically favored, it is a fast process, that is kinetically very fast. So, that is why as I told you that thermodynamics and kinetics, they should be considered parallel in dealing with rate processes in chemistry, in chemical system. So, and thermodynamics tells us that means thermodynamics tells us which direction reaction will go, and kinetics tells how quickly it will go, okay, whether it is slow or it is fast. So, that is what pretty much related to thermodynamics and kinetics. Aims for studying rate processes at macroscopic level, you have to define rate of reaction, order of reaction, and rate law, okay, and we have to examine how rates and orders are determined. So, we determine rates and orders for chemical reactions. So, we define rate of reaction, then order of reaction, and also rate law for any chemical process. And microscopic molecular level, what we want to learn here, I mean what we learned here is the predict a plausible mechanism from experimental observations, maybe rate laws, okay, rate equations. We would like to formulate a plausible mechanism. Okay, so that is pretty much what is related to the aims of this, and especially at the molecular level of understanding. So, macroscopic in macroscopic level, measurable parameters are PVT, and microscopic levels parameters are hard to measure directly. It is very difficult, because microscopically you have to pick up certain molecules, and then you have to find out what is the speed. It is difficult. Okay. So, macroscopically it is somehow it is easy, but microscopically the parameters which are important, like speed of molecules, what we talked in collision theory. So, collisions are responsible for chemical reaction to occur. So like these parameters, like speed of molecule, is hard to find out. Okay. So, anyway, these are pretty much what is related, I mean what pretty much the aims and objectives. Okay. So, chemical kinetics means, as I told you, like these things already I have talked about, that feasibility and course of reaction, like reaction rate I discussed, like this way you can like write the reaction rate, that is rate of disappearance and rate of appearance. Okay. And it is basically this rate equation is nothing but the relation between rates of loss or production of certain chemical, certain substances, maybe substrate or maybe a product. Okay. So, and we discussed reaction rates and stoichiometry, relation between stoichiometry and reaction rate, and the relation was like pretty much like this. For a general reaction you can write like this: stoichiometry, alpha, beta, gamma and eta, these are the stoichiometry. So, you can relate this for a balanced chemical reaction. Okay. Okay. Next, measuring of reaction rate. Next question which we discussed was how to measure the reaction rate, and it is not very trivial. You know, sometimes it is difficult to find out. If it is a very slow reaction, then maybe it is easy to find out, but if it is a moderately fast reaction, then maybe various methods can be employed, like one is method of initial rates, that is at the very, you can plot concentration versus time, okay, and you take slope at different times. So you can, this is concentration versus time. So that will give you the that will give you the rate maybe at different instants. Maybe there are methods that I already discussed, method of integrated rate laws. You devise the rate law and then you integrate, I mean you devise your differential equation and then you integrate to find a relation between the concentration of your reactant and the time, okay, and then you put in your necessary inputs and then find out the rate constants, okay. That may be another way. So the goal of study of reactions kinetic is the study of the chemical reaction, balance the chemical equation, write the rate law, find respective the ith rate constant and exponents using various methods like methods of initial rate, method of integrated rate laws, and so on. I discussed so many methods of finding out, and then solve the concerned differential equations, like that will end up in getting you the informations related to the kinetics of a particular reaction, rate constants, rate law, half-life, okay. And then also of course the plots, concentration versus time, maybe Ln concentration versus time, okay. Now two important facts that has to be explained whenever we deal with any chemical reaction, okay. The experimental fact is reaction rate, rate constant increases with temperature, okay. Why it is increasing? So we should have a justification of that, okay. And another important point, that 1 out of 10 to the power 10 collisions may lead to reaction. So there are so many collisions, but not all of them are effective, okay. So to react, molecules have to collide, and the collision frequencies is typically 10 to the power 30 collisions per second for molecules in gas phase, okay. And if each collision yielded a product molecule, then the reaction rate could have been 10 to the power 6 mole per second or even more. But in reality gas phase reactions have much less value, like maybe 10 to the power 1, maybe 1 mole per second, like that. So these are much less, okay. So in order to explain this fact, so we have to have justification why it is like if it is based on collision theory, then why it is so less. What are the factors? Why when temperature is increased, rate constants are increased, and if you raise the temperature, if you increase the temperature by 10 degrees, then rate constants are generally increased by 2 to 3 times, a factor of 2 to 3. So this we wanted to explain, this we wanted to justify based on certain available physical models, okay. So this is these are the two important things that we should have in our mind. So theoretical models, as I told you, that we used different available theoretical models to justify. One is very popular, that is collision theory, based on kinetic molecular theories of gas, that whenever you have a container full of gas molecules, then there will be collision between them, okay. And it is thought that collision is responsible for the reaction to occur, okay. That is the postulate, that collision is responsible for reaction. And next question comes that that whether all collisions are effective, because as I told you that there are there are only out of 10 to the power 10 one collision may be fruitful. Okay, so why it is so? So that means there must be something inherent. So that we discussed, that not only all collisions are effective. Okay, collision theory considers that such energy, I mean the energy which is required for reaction to occur, is provided by kinetic energies of molecules upon their collision. So that means for a reaction to occur, a definitive amount of energy must be supplied. And then we introduce the concept of activation energy. What is activation energy? Activation energy is the minimum amount of energy that is required for the reaction, I mean that must be acquired by the molecules or the atomic species to undergo chemical reaction. Okay. And importance here, one more important point is that the orientation is very important. I mean, suppose if you have a collision of this sort, that may lead to chemical reaction, but if the collision is like this, maybe reaction will not take place. So that means orientation factor is another important thing that we should include, and when that has been included over there. Okay. And so that means not all collisions are effective in bringing out chemical reaction. Then we introduced transition state theory, and an unobserved activated complex is proposed here. Okay, an activated complex is formed, that is the transition state, and this transition state is there in between your reactant and product. Okay, and it is thought that this activated complex is short lived, means it was thought in that way, and it is slightly reactive, and maybe out of many vibrational modes, one mode is converted to translational mode, maybe low frequency high amplitude mode. Okay, so it is short lived and it is in equilibrium with the reactant, and then slowly it is converted to product. That is, out of its many vibrational modes, maybe one is converted to translation, which is responsible for the passage from reactant side to the product side. So this way we try to justify, I mean theoretically we try to justify reaction, I mean reaction rate and effect of temperature, I mean implication of these theory. I mean we try to apply this theory to justify. And effect of temperature, of course, we talked in terms of this Arrhenius expression, K is equal to A into exponential minus E A by RT, where E is the activation energy, and we discussed what is EA in terms of the potential energy diagram like this. So this is your forward activation energy EA, this is EA. Okay, and it is clear from this expression that if you increase temperature, since it is minus EA by RT, so K is going to be increased. So using this expression, using this, and EA is called the activation energy, it is in kilojoule per mole or maybe in joule per mole, and A is the pre-exponential or maybe the frequency factor. Okay, now using this expression, we can find out the activation energy by doing the experiment, by carrying out the experiment maybe at 2 or 3 different temperatures. Okay, I mean we find out the rate constant at 2 to 3 different temperatures, and then we plot ln k versus 1 upon temperature, which will from the plot you can find out this activation energy. Okay, that is from the slope you can get the activation energy, and from the intercept you will be able to find out the pre-exponential term. So it is indeed interesting that we are able to find out the activation energy, that is the barrier height, which is a very important thing, very important parameter in chemical reaction. Okay, so we discussed elementary reaction, and whenever there is a question of elementary reaction, then comes the question of order and molecularity. So, order and molecularity is basically, order is an experimentally determined quantity. Okay. It is the sum of the power terms that is involved in the rate expression, and it can be fractional, but molecularity is the number of species that is involved in an elementary step. So, it has to be a whole number, it cannot be fractional. Okay. So, bimolecular, unimolecular reactions could be there, and we in that heading we discuss this unimolecular Lindemann mechanism and its pressure dependence of reaction that we also discussed. Then whenever there is a elementary set of elementary reaction, then comes the question of steady state, that is a reactive species which is responsible for further reaction to proceed, that is in equilibrium. I mean that will have a steady state, that is whose concentration should not change with time. So, we apply steady state approximation to find out the rate expression. Okay. And we using that we can find out the rate equation for some complicated reaction, that is having many steps that is for complex reaction. Then we discussed a polymerization reaction. Okay. So, maybe radical polymerization reaction, we discussed this thing in detail. Okay. And with all these ideas, like we came to reaction mechanism, that is mechanism for chemical reaction. Like if you think of say hydrolysis of ester. Okay. So, whether protonation of your if it is an acid catalyzed reaction, whether protonation onto the carbonyl oxygen is the rate limiting step, or the attack of your nucleophile is the rate limiting step. Okay. So, there are various ways you can find out whether I mean which one is the rate determining part, I mean rate determining step. So, from that you can tell, I mean whether your protonation or maybe the nucleophilic attack is the slowest step or not. Okay. So, that gives you the idea of, I mean that gives you pretty much what is the mechanism of a reaction. Okay. And also we talked about photochemical reactions, where photon is involved. Okay. Photon is one of the ingredients. I mean maybe you can think that photon may be your basically reactant. So, when you shine your substance with photon, maybe it is photoexcited, then photoexcited substance, I mean chemical, maybe it undergoes some reaction, maybe pericyclic reaction, maybe photochemical transformation. Okay, where photon is involved. Okay. Then we discussed catalyst and catalysis. Okay. And its role in various places. So, catalysis is that catalyst basically provides an alternate path having I mean requiring lesser activation energy. Okay. And thereby rate is increased. I mean if activation energy is less, naturally rate constant, I mean if you recall Arrhenius expression. So, if activation energy is somehow reduced, then rate is expected to be more. So, catalyst is important. So, it provides alternative path. So, catalysis and catalyst, so many types of catalysts are there, maybe homogeneous catalysts or maybe heterogeneous catalyst, that those are used in industrial synthesis, maybe like I discussed ammonia and other synthesis. Okay. So, that there means heterogeneous catalysts are used. In homogeneous catalysts there are plenty of examples, and this is role of catalyst is very important. So, we also discussed biocatalysis. Okay. There is a typo anyway, heterogeneous catalysis, homogeneous catalysis, and mechanism. Okay. Mechanism of catalysis, that we also discussed. So, when it is the question of catalysis, mechanism catalysis, we discussed biocatalysis. Biocatalysis means in that case catalyst is a biomolecule, okay, large biomolecule. It is a protein called enzyme. So, it has got a specific structure which binds, or maybe it has got a specific pocket which binds your this substrate, okay, into its pocket, and then it does the reaction, and then when reaction is completed, then it is released. So, this way it is used up. So, catalyst is used up, okay, it is regenerated and then it is used up. So, it is a cyclic way. And we also discussed enzyme inhibition, like means these inhibitors are basically they tend to impair enzyme action, that is catalyst's action. Okay. So, we discussed this in detail. So, it is this part is also discussed. We discussed fast reactions. Okay. Fast reactions means like as I told you that when the reaction is very fast, then ordinary methods like what we do in laboratory, burette, pipette, then color reactions, maybe titration, these are not very useful, because the moment you start doing your titration by taking out some amount of alicate, by that time your reaction is over. So, titrometric or classical methods are not very useful. So, that is why we had to devise alternative way. Alternative ways means like alternative techniques like flow methods, like stopped flow, plugged flow. These are the methods that I already have discussed, and it may use absorption technology, technique, or maybe emission spectroscopy. Okay. Relaxation methods are also used, temperature jump methods are used, and last one which I discussed in detail, that is the flash photolysis, and the modern version of it is laser flash photolysis. So, I discussed, and typical time resolution is much improved, but only point is that your substance that should absorb at a given wavelength. So, otherwise you cannot detect it, your product has to absorb. Okay. So, that it relies on the applicability of spectroscopic determination of the chemical, of the substance which is generated due to chemical reaction. Okay. So, flash photolysis is a very efficient method by which you can look into the fast processes. Fast means moderately fast, and its time resolution it is determined by electronics used, maybe the detector, and typical time resolution, and also of course the laser pulse width, and like it is typical of the order of several nanoseconds, like about 5 to 10 nanoseconds. Generally Nd:YAG lasers, pulsed Nd:YAG lasers are used for laser flash photolysis. So, and its time resolution is several nanosecond, okay, that is not below nanosecond. Okay. Then we talked about this ultra fast processes, because when it is the question of time resolution in flash photolysis, then we are limited by the detection system and also by the laser pulse. So, flash photolysis it is flash photolysis is it is the bottleneck, general flash photolysis. So, we have to have some modern version of it, which is called a pump probe technique, where you use even faster lasers like picosecond lasers or maybe femtosecond lasers. Okay. And using that, due to the advent of fast lasers and of course, when laser came into science, for the use of research, mankind, then the overview of detection limit, overall detection limit is much increased. Limit is increased means we can go down to faster time scale. So, that flash photolysis is the first step. Laser flash photolysis, it is a little bit further ahead, and then ultra fast lasers advent of ultrafast lasers, and their application in spectroscopy is very useful. And in this under this heading we discussed this this pump probe spectroscopy, where a pump laser is used and a probe laser is used. So, it is a 2-color experiment. So, ultrafast lasers, using ultrafast laser we can do pump probe. It may be 2 color, it may be 1 color. Okay, and because of the faster time scale, its bandwidth is more, wavelength bandwidth is more. So, you can probe for more wavelengths. And using this ultrafast spectroscopic techniques, maybe using fluorescence subconversion and related techniques, you can follow faster processes like solvation dynamics, or maybe some rearrangement dynamics, maybe excited state isomerization dynamics, that you can follow very efficiently using ultrafast spectroscopic techniques. Okay, so use of these ultrafast lasers, you can probe transition state, for which Ahmed Ziwell is awarded Nobel Prize in 1999. So, that is that is also using ultrafast spectroscopic. I mean, he used ultrafast spectroscopic techniques to probe this transition state. So, use of this ultrafast techniques, we can really probe transition state. I mean long time back, when people started to think about the mechanism, and also the theory of reaction, chemical reaction, then this transition state theory was implemented. And after a long time, after waiting for a long time, after the advent of ultrafast lasers, we are now able to look into this transition states by means of ultrafast, by using ultrafast spectroscopy. Okay, so it's a ultrafast spectroscopy is a nice gift to mankind for probing such fast processes, which is completed within the persistence of vision, much shorter time. Okay, maybe several million times faster than the persistence of vision. Okay, so long time back, people even could not think of a technique which can probe maybe millisecond process, but now you think it was like 10 to the power minus 3 seconds. Now it is 10 to the power minus 15. Okay, maybe sub femtosecond, maybe attosecond techniques. Attosecond spectroscopy is emerging. Okay, so attosecond techniques are slowly emerging. Means it is faster than your femtosecond. Okay, so we discussed probing, probing of transitions. We gave some example. Okay, next we discussed this reaction dynamics. Okay, now why do we need, we discussed many things. It appeared to you that maybe it is complete. We should not think of anything else. Maybe measuring rate constant, then probing ultrafast processes, fast processes, maybe probing your transition state. That's all we can think of. But one important point that we must look into is in a typical kinetic study, rate constant, which is determined, what we determine in laboratory, like using burette pipette, maybe doing some titrimetric method. The rate constants which are determined is highly an average quantity. Okay, it's an average quantity. It's an ensemble average quantity, the combined outcome of large number of individual collisions between reactant molecules. Okay, so there are number of collisions. So it is the overall thing. Okay, whether some collision is very vigorous, or maybe some collisions are very less effective. So, everything, it is the combined, combined effect. Okay. So, everything it's in average form. Okay. It is basically an average quantity. So, we have no idea. There is no microscopic description, as I started with, that there are two aspects. One is microscopic aspect, another is macroscopic aspect. So, determination of rate constant, it's an average quantity. So, it's a macroscopic aspect. So, we do not have any idea of your microscopic things like speed. Okay, at actually understanding at the molecular level, we have no understanding. On the other hand, this chemical reaction dynamics study has the aim to understand chemistry in detail. Okay. So, we want to know chemistry at the molecular level. Okay, not in the average level, not in the gross level, but in the molecular level, at the molecular level. Okay. So, it aims to understand chemistry in detail by probing chemical reactions. Okay. So, now we have to probe chemical reaction at a level of single reactive collision between molecules. Okay. At a level of single reactive collision between molecules. Okay. So, we want to approach to understanding at the molecular level. Okay. And it is possible to control the speed, the quantum states, like as I discussed, like quantum state selection, even orientation of the colliding molecules. Okay. To find out the effect of these variables. So, these are the variables. Okay. I mean, speed is one variable, quantum state, selected quantum state, then orientation. These are very important variables that can control the chemical reaction. Okay. So, that we want to have a clear cut understanding at the molecular level, means how this is going to affect the overall thing, and preferably in the gas phase it is easy to control. Okay. So, this study gives us insight into basic physics underlying chemical reactivity. Okay. So, this way we want to probe the basic physics underlying chemical reactivity. I mean from purely physical aspect we want to study. Okay, what is the orientation? I mean, what is the orientation factor, or maybe what is the speed factor, or whether the reaction occurs in the ground state, or maybe occurs in the vibrational excited state. If it occurs in the vibrational excited state, then what happens? Like I discussed one thing like early transition state and late transition state. So what is happening when it is vibrationally excited, or it is translationally excited? So, these are the things that gives you an important idea about the nature of the potential energy surface which is involved in the chemical reaction. So, potential energy surface is important. So earlier when we talked about energy of activation, it is basically giving you the barrier height, but it does not give you any insight of the insight of the nature of the potential energy surface involved. So, these studies, I mean these reaction dynamic studies will give you the potential energy surface, I mean the nature of the potential energy surface involved, whether it has got single minima, or it has got a double minima, or something else, whether there is a level crossing. Okay, I mean whether there is a crossing with an unbound state, then what is going to happen? Like I gave you the example of sodium iodide decomposition. There is a crossing between this ionic potential energy diagram and also your covalent one. Okay, at certain distance they are crossing. So, if your wave packet is moving back and forth, and if it is appropriately excited, I mean in the vibrationally excited, so that it can cross, it can reach this crossing point, so that your ionic surface, I mean ionic from it, means the your wave packet can be transferred from your ionic surface to the covalent one, and thereby it may undergo dissociation. So these aspects, you know, are very important. So this gives you the idea of the potential energy surface. Okay. So looking at the potential energy surface is very important, and a very important aspect in molecular dynamics. Okay, I mean molecular reaction dynamics. So this is very important. So that's why we intend to study reaction dynamics. So it gives you the idea of the, I mean, nature of the potential energy surface involved, and what is the minimum energy path. Okay. So and means so these are the things that we can know. Different mechanisms we discussed, like harpoon mechanism. Okay, as for example harpoon mechanism we discussed, then you know, rebound dynamics, then and so on, and various experimental techniques like molecular beam we dealt with, then also like ultra fast techniques. These are very important with respect to, you know, studies of reaction dynamics. So we all we dealt with these things. And molecular, whenever it is the question of molecular beam, then it's a crossed molecular beam experiment. Okay. So crossed molecular beam, like two beams are you know, cutting like this, and your detector is somewhere over here, so that you can detect the scattered product. Okay. And when it is the question of potential energy surface, we can have a, you know, quantum mechanical way of calculating it, although we have not discussed that in detail. So molecular beam experiment and other experimental techniques and special detection techniques, that we all you know, we discussed all these things. Okay. And also the how this beam angle, you know, changing the beam angle, what is the outcome, that we also have discussed. So and also probing the transition state. Okay. These are the important, you know, things that we discussed under the heading of your molecular reaction dynamics. And lastly, we also talked about this corrosion kinetics. I mean, not in detail, but we gave you the idea of corrosion kinetics. I mean, how to measure corrosion, etc. So so these are the things that we have talked about here. So at the end, it appears that, so we go back to that slide, I mean early slide again, that that chemical kinetics, it is the aspect which an important aspect in chemistry that affects everyday life. As I told you, this movement of an insect, it is also a chemical reaction because it requires energy. Okay, we move from one place to another. Okay, it requires energy. So that energy is given by some reaction. That is, some reaction happens within our body, I mean within cell, that generates the energy, and that is used up, okay, to do some work. So again, it is thermodynamics. So because of chemical reaction, energy is released, and that is used up for doing some work. Okay, so it is, you know, conversion of chemical energy into, you know, mechanical energy. So here also means, like when we require to work fast, then fast generation of your energy is required. So that means there must be some machinery which controls, means which, you know, measures the need, which you know, which monitors the need, that we need more energy. I mean, means energy output, I mean rate of output energy, I mean rate of giving out energy is more when you need to work fast. Okay, so again that means again it is kinetics. So we need faster kinetics. Okay, so that's why kinetics is a very important thing. Like something is growing, like we grow up. It is also it has got also kinetics. Okay, so so these are very important thing. These are very important aspects. I mean, kinetics, and especially it is a broad heading. It is, you know, rate process. Okay, so how these rate process influence our life? Okay, how this rate process influence you know, other processes? Okay, and how this rate processes can be influenced by external agents. Okay, how can we monitor? How can we monitor such rate processes? Okay, can we see the transition state? I mean, can we see the transition state which we have postulated long time back? So we answer is yes. So we have been able to probe. Okay, that is the ultimate answer. Okay, that we have been able to probe. Catalyst is another important thing. Okay, and that changes our life. Okay, anyway, so that's all about this course. So I hope you enjoyed, and if you have any question, you can write to me. About this topic. So you can write to me. My email address is mintu@kgp.iit.kgp.earnet.in. So questions are welcome. I hope you enjoyed this series of lecture. So thanks for your patience. I wish you all the best. Thank you.